Hello everyone, this is Purya Ahmadi, PhD in Mechanical Engineering. Today I'm going to tell you about some introduction to TRNSYS software, and we are going to go through solar PV panel IV curve. So let's get started. As I already discussed about the TRNSYS software, this is the screenshot of the TRNSYS software. In order to start a project from scratch, we just click on a new project here. Then I select empty TRNSYS project. Then this is the environment of the TRNSYS that I just want to start with. So before just starting, we knew that for any type of projects that we want to get started with TRNSYS, we need to first determine about the weather data that we have. So for example, in which location we are going to install that solar PV panel. So that is really important for us to have that weather data, including the temperature, humidity, wind velocity, solar radiation, and so on and so forth. So as you can see here, there are several options on the right, all the way down from applications, cogenerations, and all the way down here at the end of this types, you will see weather data reading and processing. If I just open that one here, you will see standard format and user format. If I click on the standard format, then I will select TMY2. I will just drag type 15.2, then I will drop it here. So this is where I need to just calculate. Okay, you might ask, what are those options? So for example, that TRY is for the average of 2004, and German TRY, they have more the weather data in Germany and European countries. So, and the metronome files, for example, let's say that you are trying to model and simulate a transient simulation for the PV panel for a location where the weather data is not available. So what you can do here, you can just connect metronome data, then get that data and incorporate it here in TRNSYS software, and later on you can just simply use it. But leave it for now. I just use TMY2 because I want to have the weather data in the United States. Okay, so I just closed this part here. Then how to select a location using type 15.2. If I double click on that one, you will see several options there. If I just click on external files, then you will see that it is selected Madison in Wisconsin by default. This is where TRNSYS software is developed. If I just click on browse, then it just goes to where I installed my TRNSYS, as you can see here. Then if I click on the weather data, then since I already selected TMY2, I click on TMY2. As you can see, they just all started with US, so meaning that they are all about the locations in United States. So I just want to select Philadelphia in Pennsylvania. Okay, let's go all the way down to USPA, standing for Pennsylvania. If I go down all the way here, so in Pennsylvania, I have Philadelphia and I have Pittsburgh. For example, let's use Philadelphia here. Then I click on that one. As you can see here, Philadelphia with that specification is selected. So I just close it there and leave it there. Then here, I just need something to just plot the specification of the weather data that I want. So in this case, what I need to do, I go to output, then I go to online plotter with file, and online plotter without file. So I don't need the file right now. Then I select type 65D. I drag it here and I just drop it there. So, or at the same time, I can change the name. If you just double click on that one, no, not double click on that one, if you just put the cursor there, then their data. And this one here, if I just select the text, plot. Then I need to just link these two options first. If I go to the left side, this is log, this is link. If I click on this link, then I select weather data to my plotter, right? So here, as you can see, there are several specifications from the left part, like dry bulb temperature, dew point temperature, sky temperature, and wind velocity, and all the way down. Let's say I'm gonna plot dry bulb temperature on the left axis, and I just click it. Then, for example, wind velocity on the right axis. Okay, so as you can see, they just changes. The colors are changed to black. So it means that they are already activated. Then if I just hit an OK, then I have in this page, so I can just look at how I can select those data. Okay, another specification which is really important, I use the cursor on the left left here, select. Then I just need to click on plot option. As you can see, there are 4 tabs. So on the first one, where the parameter is, you can see the left axis minimum and the left axis maximum. So the left axis, if you remember, was the temperature. So since the unit of temperature is Celsius, I will just, limit the maximum amount for about 35 degrees Celsius. And the wind velocity, which was the right axis, I just limited to 20 meters per second. Then, if I go to special cars, you will see that the left axis title is temperature, but right axis title should be wind velocity. I will just correct that one as well. Wind velocity, and I will change the unit, meter per second. Then that's for now. Then I go to the setting to just set the time. So here, as you can see, I have the starting time from 0 hour, which is January 1st, and this is the stopping time. By default, it is selected by 168. So I just want to show it over a year, and as you can know, 1 year is equal to 8,760 hours. So the simulation time step, it is by default 0.12. I will just change it to 1 hour. So then I will hit OK. So this is the time for running the simulation program right now. If I just click on the run, then you will see what will happen to the temperature and the velocity at the same time. Okay, I'm not going to just exit. Then here, I just want to remove the black background. If I go to plot option, if I select white background, you can see this is what I have there. So again, you might ask, oh, I have red and purple. Which one is temperature and which one is velocity? So it is shown there. So the purple one is wind. If I deselect that, it is going to be wind. It is going to be the temperature during 1 year, right? Then if I want to deselect temperature, I have nothing here. So if I just again reselect wind velocity during a year in Philadelphia, I can see that one. So again, there are several options here. For example, if I right click on the left y-axis, you will see that I can again change it here. For example, change it from 0 to 40. Look, I already had then options to change it with the online plotter, or I can at the same time change it there. So this is really important for us when we want to look at the output. But here, this is just an introduction. What I'm going to talk about today is to draw your attention on how I can just plot a performance curve of PV panel. So let me just pull up a PowerPoint that I have here. As you know, the performance curve of the PV panel, based on your knowledge, is I, which is the y-axis, and voltage is the x-axis. So this IV curve, the blue curve, is the performance curve, IV curve, and the purple one here, look, is the PV curve. As you can see here, and at the same time, this is the maximum power point. This is where the PV panels are operating, so at their higher best performance conditions. So as you can see here, this is IMP means maximum, and VMP means maximum voltage. And that point is short circuit current, and this one is open circuit voltage. So again, for the TRNSYS, let's pull up the TRNSYS and go to select PV panel. So I just want to delete this one. I just click on that one, then press delete from my keyboards. Then I just, move there. If I go to electrical, then all the way down, I have PV panels. So I have advanced model and I have basic model. So what are the differences? The advanced model has with MPPT, maximum power point tracker, and the basic model, again, no MPPT and with MPPT. So they are just mostly similar to each other, but there's like a little bit a difference in some features. Let's say that I'm gonna just select no MPPT for now, then just to look at that option. If I select that one, if I click on that one, you will see that in the parameters, I need to consider several options here. Those options are short circuit, open circuit voltage, reference cell temperature, and other specification of the PV panels. So I just already selected a catalog from one of the solar manufacturers. As you can see here, there are several specifications of the panel. This is the performance curve of the panel that was already shown to you. And here, I'm just going to select these electrical parameters here, where you can see the maximum power voltage, power current, open circuit voltage, and short circuit voltage. So let's enter those data here. For example, short circuit current. Okay, short circuit current here is short circuit current. Short circuit current is 8.85. So let's enter that. 8.85. 8.85. Open circuit voltage. Open circuit voltage. Open circuit voltage is 38.33. 38.33. 38.33. And what is the reference cell temperature? As you can see here, the reference cell temperature, as it is shown here, is 25 degrees Celsius, which is already implemented, 25. And reference insulation is 1,000. As you can see, reference is 1,000, so that is okay. Let's go to open circuit voltage. We already entered that on. Maximum voltage, okay, VMP, maximum voltage. Let's find it here. Module current at maximum power. What is okay here? Module voltage at maximum power. So maximum voltage is maximum voltage is here. 31.46. 31.36. And similar to that one, maximum current IMP is maximum current is 885. Oh, sorry. So short circuit voltage is 9.23. Okay, let me call it short circuit voltage. Short circuit 9.23. 9.23. That was maximum current. Where is maximum current? Module current at maximum power. This is that one. Maximum power is 8.85. 8.85. Okay, we have another one which is called temperature coefficient of ISC. What that is, if I go down, you will see that this is the temperature coefficient. So as you know from your background, you need to just brush up your minds. So when the temperature of the PV panel increases, the performance, the voltage, the performance will drop. So that is what we can see here, ISC condition. So temperature coefficient ISC, let's enter that. Temperature coefficient, where is that? Temperature coefficient of ISC, so A over K, here is the temperature coefficient. Let me just use that. Temperature ISC, temperature coefficient of ISC, and temperature coefficient of VOC, okay? What if VOC is minus 0.30 minus, let me just write it here, VOC, because I don't want to just pull up this PDF file, so because it is taking time, VOC is minus 0.34, and ISC is 0.044. So let me just enter these two values here. Temperature ISC is 0.044, and VOC is minus 34. Again, here is number of cells wired in series. So I have 1. As you can see here, I need to just change these parameters as well here to see that. Okay, so we just entered those information, and module area, as you look at here, the area is panel size is 992 millimeter times 160. That's why I entered 160. So number of modules in series 1, and number of modules in parallel is 1. So this is okay, but if I just click on the input here, as you can see, this is the load voltage that should be entered as well. So how can I get that load voltage? If I look at, for example, this load voltage and the power, for example, since this one is the one that MPPT is not selected, I need to select one voltage, for example. Let's select 25. Then for the 25, I need to have 200 and something. So that's why for now we entered 25, right? Then I just close this one. So again, what about another input? So you might ask, okay, what about beam radiation, sky diffuse radiation, and all of those? So I will just enter those from the weather data that I have. Again, I use that link to just connect this one. So I just connect that one to one of the information. So ambient temperature, I select dry bulb temperature. Beam radiation, if I go down, here is the beam radiation. Beam radiation for the surface, I just go all the way down up. Sky diffuse radiation is the sky diffuse radiation for surface. Ground reflected diffuse radiation, ground reflected diffuse radiation for surface. Array slope is the slope of surface. Incident angle of beam radiation is angle of incidence for surface. And load voltage, I already entered 25, and flag for conventional promotion, so I just leave it as it is. Then again, to just have the power output, I just need to again link the output of the PV panel to that one. So as you can see here, I have array voltage, array current, and array power. As you can see, you might ask why there are two array power. One is watt and another one is kilowatt. So just let's select the first one, then I connect to the left side. So as I told you at the beginning of the video, if I click on that one, then I go to here to limit it, as you can see here in the catalog. So the maximum is less than 300, That's why I limited under 300 for the left axis. So since I do not have anything on the right axis, I leave it as it is. Then if I click on the setting to set it for 1 year, so 1 year from 0 to 8,760 hours, then stopping time and stopping criteria is 1 hour, then I click OK, then I just run the simulation program. As you can see here, since this is the transient behavior, so the maximum voltage is somehow 240. So if you look at here, the voltage 25, this is the voltage, so 248, 40 something over there. And as you can see, so we can just simulate that one. So this nicely shows this condition here, as you can see. So, but again, you might ask how I can sketch this IV curve or this PV curve. So I'm gonna just tell you in a moment. So I'm just gonna close this one here, but at the same time I'm gonna just show you what would happen if I select the one with MPPT. If I select this one here, as you can see in the input, there is no voltage. So it means that with MPPT, so it already calculated at that maximum power point tracker. So it means that that point. So that's what I just wanted to highlight, the difference between the one with MPPT and that without MPPT. So let's just leave it with without MPPT, maximum power point tracker. So here, in order to have that one, I'm gonna just show you in a moment how to do so. So here, as you know, I'm gonna just plot power with the voltage. So it means that I need to change the voltage because the one that I already showed you is transient. So it shows you in 1 year, which is almost 9,000 hours. So in order to do this, what I'm gonna do, I just want to delete this one here. I just move it a little bit on higher up. Then what I'm gonna do, I need something as a counter. So to count, like I call it calculator. So if I go to assembly, if I select insert new equation, just click it here, then what I'm gonna do, I need to provide voltage. So the voltage according to this should change from 0 to almost 40. So the counter here, I go to the output, I click and I call it voltage. So this voltage should be equal to, okay, I need to start from 0. So what makes it easier for me if I count it with time, because I start the program with 0, 1, 2, blah, blah, all the way down to a couple thousand. So if I change the time and if I want to make it just more accurate, if I divide time by 100, so it means that if I want to change the voltage from 0 to 40, so the time should be counted from our 0 to 100 times 40, which is 4,000, correct? So it means that I need to just connect equation. Let's change the equation to V, for example, because I know this is V. Then if I link that one to the array voltage, as you can see, I will select voltage to load voltage. But again, you might ask, what about those conditions? So if I don't enter those, you will see this program is not gonna work. Look, I'm not gonna have any numbers here because, why? Because that is not given to the program. So in this case, I already run the program and I already entered some of the inputs. For example, beam radiation for 1 day in May is, the number is 2819, and sky diffuse radiation is 683. So ground reflected, I don't need it. I just need incident angle of the beam radiation, which is 14.27, and the reference temperature is fine. So in this case, I have, as you can see, look, I have all those data. So array slope, I can just place it a number, or I can just leave it like that, so it automatically optimize that one. But for now, let's do it here. Array, where is that? Array slope, let's say for example 20 degree, 25 degree, but that is okay, it will work. So again, here I need to just change the program from 0 to 4000, because the setting was 40 times 100, because the equation I divided the time by 100 to be more accurate. So if I run the program, as you can see here, look, the same plot is obtained as the one that I have in the catalog. Look at here, this is for the radiation of 1000, look, for the reference condition. So it's almost between 250 and 300, and here is 250 and 300, as you can see. So if I want to enlarge here, if I select here, then I can have those data. Again, so this is, of course, is not temperature. Can I change it here? No. If I double click, no. So what I need to do, I need to go to this one here, go to special code, left axis is not anymore temperature, is solar, sorry, it is power, and the unit is watt. And again, if I just run the program, you can see the unit is already corrected, and it is that one here, and you can see that one. So let's add another one here to the right axis here. So let's show array current on the right axis to see if I can get this plot here, one of those. So in this case, I need to change the unit. So current is in the order of 0 to 10. So let's change the unit to the right axis maximum. Let's limit it to 10. Then run it one more time. Then, as you can see here, look, that point, this is IV curve. If I just enlarge that point, look, at that point where the voltage and amp is maximum, this is causing the maximum point, which is at that point, because in this point this is the maximum voltage and the maximum amp. So as you can see here, if I just remove that one, this is just the power. If I just again reselect that one, this is I curve. So again, you might ask, okay, why it is 300? No, this is for the right axis. Right axis is around 9. Just let me pull up this one. Is 9 point something here. This is again, let me just enlarge that. It is 9.88, right? Close to 10. So this is again 9.88. So depending on a little bit difference here, but as you can see, we have all these data here. So you can then use this PV panel for simulation of any renewable energy system that you want. So I will continue with next sessions. Just for now, thank you very much, and I hope you just learned the basic introductory stuff about PV panel. Thank you very much.